And as you might have heard me say, we still have part 3 to do, but actually we're going to do part of part 5 and then go on to part 6, and you'll see why. So remember that was that change in the labs that we're doing tomorrow. We're doing the one that's got the word nomenclature in it. Okay, and so hope you got that set for tomorrow, Thursday's lab. Okay, so we've been talking about, and I know you've been exposed to this idea of ions. Atoms will lose electrons or gain electrons to get a complete octet. And actually, we talked about something called electronegativity last time we were in here on Monday. And electronegativity is the tendency for an atom, if it's bonded to another atom, to either just, if it's got a high electronegativity, it's going to bring electrons to itself. If it's got a low electronegativity, it's like, hey, dude, all right, electrons, I'm fine without them. So as we kind of look at the JAG here, the JAG is separating metals from nonmetals. Okay, you can see that actually, with regard to losing electrons, that's what that arrow is showing you. With regard to losing electrons, let me show you what I mean. Okay, the metals, lithium, beryllium, they will lose 1 and 2 electrons respectively, and we'll talk about this, to get the rare gas configuration like helium. Neon, argon, krypton, those are all rare gases. Okay. So if you want to skip down here to rubidium, strontium, indium, tin, okay, they will lose electrons to get the rare gas like krypton. Okay, that's kind of what we're showing you here. Again with the JAG then. On the other side of the JAG, we have nonmetals. And nonmetals have high electronegativities. Okay, that means if you put them next to something else you're going to bond to, actually they're going to bring electrons into themselves, high electronegativities. And so it's possible we're going to be kind of taking off on this idea that electronegativity difference is high enough that they actually abscond onto electrons and become negatively charged. So as we look at a period of here, these 3 nonmetals in the third period, excuse me. Second period, final answer. Okay, yeah, boron, carbon, or nitrogen, oxygen, and fluorine are in the second period. So what they do is pick up electrons to get a complete octet like neon. Okay, phosphorus, sulfur, and chlorine pick up electrons to get a complete octet like the electron configuration of argon, etc. Okay, so that's kind of where we're at. I'm going to dive into that, say that in a couple of different ways. So after the lab and after this topic, we're going to kind of switch gears to, from ionic compounds, which we're talking about now, to talking about covalent or molecular compounds, and we're going to end up drawing Lewis structures for them. But we can actually draw a Lewis electron dot structure for atoms like this. And just kind of showing you the nonmetals in period 2. We've kind of established that. Okay, period 2. As we draw the symbol for the element, okay, kind of think of in that symbol being the nucleus of the atom and the non-valence electrons of that atom. One of the things we talked about before is that you know the number of valence electrons that an atom has if you look at its, using the old convention, if you look at its group number. So for instance, carbon is Roman numeral 4A. Okay, it has 4 valence electrons. 4, okay. Nitrogen. It's a 5, Roman numeral 5A, has 5 valence electrons. Okay, you get the idea. Okay, so as we look at these Lewis dot structures, think of those electrons as being the valence electrons. And of course over here, neon is a rare gas, and it is in 8A, so that is that magical octet again. Okay, so helium is atomic number 2, so a neutral helium atom has 2 electrons, so honestly that's where we're kind of showing you the helium actually is a rare gas, and it's one that's a rare gas without a complete octet. It's the only one. Okay, so let's look at kind of this process of atoms becoming ions. And we said that metals like sodium will lose, actually they'll lose all of their valence electrons and become positively charged. So if we dive into this a little bit, okay, sodium is atomic number 11, okay, so sodium atom has 11 protons. Okay, if it's neutral, like we're showing you here on the left, 11 protons. Okay, if it's neutral, it has 11 electrons. Okay, it loses 1 electron, and now it still has 11 protons, and now it only has 10 electrons. Okay, that's why it's a +1 charge. That's kind of how that works. They're off balance. Here in this part, in just a minute, we're going to actually write the electron configuration of this thing. Okay, the electron configuration of this thing. And actually, this is the sodium, what we're going to call cation. If something's positively charged, it's not just an ion, it's a cation, positively charged. And we're going to come up with electron configurations. One thing before I move on is that when you're dealing with a species, whether it's an atom or a polyatomic ion, something that's charged, we generally put it in brackets and put the charge outside the brackets. Okay, so fluorine is on the other side of the jag. So fluorine is a nonmetal, and nonmetals tend to pick up electrons. Specifically, fluorine is in the 7A group, and so it has 7 valence electrons. You see them around there. And I sometimes kind of think of it as like a little parking garage, where it actually has one little open spot here, and that's where that electron goes. Okay, but like you saw a little bit ago, this whole idea of kind of drawing these Lewis structures of atoms, there's no really significance to kind of the east side, okay, or the west side, or the north side, or the south side. It's just simply convenient to kind of show an octet with kind of the 4 sides. So if we were going to kind of inspect what's going on here, fluorine is, I don't have that one memorized, is atomic number 9. So it has 9 protons in its nucleus that's going to stay there. And when it's neutral, it has 9 electrons. It picks up 1 electron. So now it has 10 electrons and 9 protons. Okay, so of course, if you do kind of the little math there, it's kind of got a net -1 charge. That's how that works. But let me kind of, while I have this, check this out. So now it's got 10 electrons. You know, what else has 10 electrons? Well, if it's neutral, neon has 10 electrons. So now we say it's, and the term is isoelectronic. I have it coming up on a slide, which is also a nice term to put on a test. Now when fluorine picks up 1 electron, becomes this anion, negatively charged ion called an anion. It actually is isoelectronic with neon. Okay, so I think only one more. A neutral sulfur atom, actually sulfur is in 6A. Oxygen and sulfur are both in 6A. So you see the 6 valence electrons represented there. It's got 2 sparking spots. It picks up 2 electrons. And in doing so, it now runs around with a -2 charge. It still has the same number of protons in the center. Now it's got 2 extra electrons, so it's -2. And you can see at the bottom there, it actually caught up with the rare gas. This is the way I think of it. It caught up with the rare gas in group 8A in its same period. So beyond sulfur is argon. See how that works? Okay. So ions. So ions are something that lose electrons or gain electrons. We said that metals tend to lose electrons, an electron or electrons. Okay, and in doing so, metals, as they now have more protons in their center than electrons, they become positively charged, and we call those cations. Not to be confused with a cation. So the nonmetals, we said, to get a complete octet, it's a lot easier to pick up 1, 2, or 3 electrons. And then they have a net negative charge. And they are called anions, not to be confused with anions. So in my own mind, and I don't know if you'll find it helpful, but cations are generally metals, okay, and anions are nonmetals. You know, and it makes sense if it's kind of in context of what you either knew before you came to this class or context of what we've been talking about. Metals have, just to kind of join in what we talked about on Monday, metals have low chi, electronegativity. Nonmetals have high chi. I like that phrase, high electronegativities. Okay. So, sometimes students will, and I didn't bring my black and white copy, but like for your lecture notes, one side is the periodic table, and you always get one of those periodic tables for a test, and you're going to get one for your Unit 4 exam. Sometimes at the top of Group 1A, students will write a +1 charge, and that's because they all form +1 cations. Group 2A form +2 cations. And Group 3A, now here's the problem with 3A, quite frankly, and I'm disturbed by it, but I get over it. With 3A, you start to run into the JAG, and I don't have a good workaround for that, okay? But for 3A, you start to run into the JAG. So you see here that I'll hang what I'll say hang my hat on, and you'll see why I use the phrase hang my hat on it. But for at least aluminum and gallium, and I think indium and thallium, they form a +3 charge. But notice what's on nonmetal, or at least a metalloid, is boron, right? It doesn't necessarily form a +3 charge. Okay. So let's look at how the electrons are configured around cations, where electrons are lost. Now, I know I didn't emphasize it in this lecture, but I need to say now that when you compare the neutral atom with its cation, when it loses electrons, the electron or electrons are going to be lost are the valence electron or valence electrons. That's something we've already talked about. Valence electrons are in the highest n. Okay, so the highest n here is 3. So when we write the electron configuration for the sodium cation that's lost 1 electron, it's going to be that 1 electron in the 3s. Sometimes on a test, I want to think maybe a chemistry graduate entrance exam, they actually will ask you how are electrons configured for a cation. And to me, the only way you can come up with that is to first write how electrons are configured around the regular atom. Identify your valence electrons and then subtract them. So aluminum is atomic number 13. So these are how the 13 electrons are hanging out around a neutral aluminum atom. So again, in order to really kind of have the best shot at saying, well, what happens when you lose 3 electrons, I think you have to say what is it like when it has all of its electrons. So the highest n is equal to 3. So actually, the 3 electrons that are going to go are here. Okay. So rewrite that. So any questions about that? This is sometimes where it gets a little, I'll say awkward, but students want to say, because I really like the abbreviated rare gas notation. I am really down with that. But sometimes students, especially when it comes to saying how electrons are configured around a cation, they're like, hey, Mrs. Snipes, can I just do this? Okay. And I usually try to, in so many words, say no. If that looks like it doesn't give enough information, you're right. Okay. I mean, it's true. So I don't know how to answer that question. Hopefully you won't run into it on the test. But if you do, just think of this conversation. All right. So in the case of aluminum just now, we said that there were 3 subshells that both had the energy level N is equal to 3. Two subshells, sorry, that had the energy level N is equal to 3. We had 2 electrons in the 3s and 1 electron in the 3p. But frankly, if you want to rewind it, actually it was the p. I'll just write the valence electrons for aluminum, if I can. 3s2, 3p1. Technically, the value, you guys remember, L value of an S is L is equal to 0. For p-type, L is equal to 1. So what this is saying is that the one to jump ship first, if you're looking at them piecewise, is this one goes first. Okay, and then these two strip off. There's actually something called ionization energy, and that's one of the things we're going to actually come back to. Okay, but ionization energy is a measure of the energy that is required or released when you kick off electrons. So that one will go first, technically. So iron has 26 electrons if it's neutral. So using the lowest N plus L rule, which is what you're going to need to do for your unit exam on December 4th. Did I read that right? I don't know. It's after Thanksgiving. Okay. So you're going to want to use the lowest N plus L rule to say how those 26 electrons are organized. So the thing about iron, and we'll be hitting this tomorrow, is some metals like iron form more than one cation. Okay? In one case it loses 2 electrons, in one case it loses 3 electrons. But if you've done this correctly, you should be seeing 2 valence electrons right here, right? The highest N, N is equal to 4. 2 electrons in the 4s subshell. Okay, so those are actually going to be the one that goes when we talk about the iron, the Fe plus 2 cation. So the Fe2 plus cation has lost all of its valence electrons. We talked about exceptions to the lowest N plus L rule, and we said those exceptions occur on purpose to get a half-filled either D or F subshell. So can you see where this next step, where if we piggyback from the Fe2 plus, kick off 1 more electron to get an Fe3 plus, notice we have some options here. We have N is equal to 3 in 3 different subshells, but we have an S value of 0, 1, and 2. So actually, one of these 6 electrons go to form the Fe3 plus cation. So I mentioned that we talked about why there are exceptions to the lowest N plus L rule. And so can you see where kind of making this one leap from the Fe2 plus to Fe3 plus, now we have a half-filled D-type subshell, which that's a happy little cation too. Okay? So again, I think in order to have a fighting chance at writing the electron configuration for a cation, you have to write the neutral atom first. That's a good question. Chelsea's asking, do you think you should reorder it so you can actually see the valence electrons? Probably. Or if you don't reorder it, at least recognize that a lot of times students will, kind of what you're suggesting, let's say students, adults, because students are adults, students or non-students won't recognize where those valence electrons are. And they'll just say, oh, I'm losing 2 or 3 electrons. They'll take them, in this case, off of the 3D, and that's not right. So you're on the right track. Okay. So those nonmetals then pick up electrons to get right the rare gas in their same period. I like nonmetals better. I don't know. I just think I like that whole adding electrons and becoming negatively charged as to losing electrons and becoming positively charged. I can see it better. So to kind of summarize what we have, I'll put all these up here. Non-metals, there aren't very many of them, are there? They're few, but they're proud. They're important players. So the 5A non-metals pick up 3 electrons, get an octet. The 6A pick up 2 electrons, get an octet. And the 7A, which are the halogens, actually, pick up 1 electron to get an octet. Yeah. So sometimes what students will do on their periodic tables is mark out up. And I usually I skip the 8A and I go to the 7A and I write -1, because those non-metals anyway form a -1 charge. Those would be halogens. And I go over one period to the 6A and put a -2 on top, to the 5A and put a -3 on top. And that's what charge they form. Sometimes students prefer to up there put how many electrons are lost or gained, and then it's just the opposite. So, your choice. So let's look at electron configurations of those negatively charged anions. So chlorine, and going with, and these actually you can use the abbreviated rare gas notation, I think. I say that, but if it looks too brief, then expound. So beyond the 10 electrons of neon, chlorine has these 7 electrons, so it's got 17 electrons. So it picks up 1 electron, of course, it's going to go in the 3p, so now it's neon core 3s2, 3p6. I guess what you would not want to do, hopefully we're all on the same page right here, is put, although I love the name of the element argon, you would not want to put brackets AR. Okay? But that's what it is. Picking on another one, also in that period 3, phosphorus has 5 electrons beyond neon. To get a complete octet, it needs to pick up 3 more electrons. And in doing so, picking up 3 electrons to get the complete octet, now it runs around with a -3 charge. That probably works for you. So the complete octet that we've been talking about is kind of reflected up there. Remember that superscript is the number of electrons in that subshell. All right. So I already used this term, isoelectronic. I like to use the word generic species, because species means I don't know if it's a neutral atom, or I don't know if it's a negatively charged anion, or I don't know if it's a positively charged cation. If you just use the word species, you cover ions and atoms. But isoelectronic things have the same number of electrons, and they are hanging out in the same configuration. So actually, all of these are kind of around neon. If you find nitrogen, oxygen, and fluorine, they are actually in the same period as neon. And if you find sodium, magnesium, and aluminum, they are in the next period as neon. They lose electrons to become isoelectrons. So tomorrow's lab, I don't know if you had a chance to look at it, but you will be dealing with a lot of these. Bi in binary means 2. Binary ionic compounds. So basically where you have 2 elements that have come together to make a compound. And what you're going to see is in tomorrow's lab, or the rest of the lecture, is consistent with what we've been talking about. Of those 2 elements that make an ionic compound, the positively charged cation is going to be a metal, and the negatively charged anion is going to be a nonmetal. This little bit about making sure that the formula for that compound is neutral, we'll talk about that. There needs to be the pluses from the cation need to be outweighed by the negatives from the anion. We'll talk about how that works. I'll talk about my crisscross rule. Okay, so it's funny because this is sodium and fluorine, okay, but if you look where fluorine is, actually underneath fluorine is chlorine. So fluorine, chlorine, blah, 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 halogen. So actually what we're talking about with sodium and fluorine, we could have just easily been talking about chlorine, and it's 7 valence electrons. But we kind of talked about this stepwise process, okay, where sodium wants to lose its valence electron and become a +1 cation. Fluorine wants to pick up a valence electron and get the complete octet, let's see, neon. Okay, so an electron is transferred. Okay, after an electron is transferred, then you have this +1 cation and this -1 anion. And a lot of times you'll hear me say the dot, dot, dot. That's how I think of chemical bonds that are ionic bonds. So here is my dot, 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 dot. Okay, that's my ionic bond. Okay, so sodium fluoride. Neutral formula. So here now we're switching from fluorine to sulfur. And the thing about sulfur is now it actually has 2 spots. It needs to pick up 2 valence electrons to get its complete octet. So now actually it needs to have 2 sodiums that each give up an electron. Okay. And we'll be talking soon or hitting this tomorrow why this is. So in order to have a neutral this compound actually has 2 sodiums. Na2 has 2 sodiums, and it has 1 sulfur. Okay. When we talk about a neutral unit, can you see where this whole unit, this Na2S, has 2 pluses and 2 minus. So it actually is a wash. This thing is neutral. Okay, going this route. Okay. So, on to part 6 for now. It's nice to get on to part 6 a little bit because it makes our tomorrow a little easier. Be sure while I'm thinking of it, if you don't usually, be sure go ahead and throw your lecture notes in your bag along with your lab notebook tomorrow, because I can't decide how far we get today in part 6. We might kind of finish up a little bit of part 6 and knock out that lab. So we talked about ions, okay, where an atom, actually, if it's a metal, it's going to give up an electron or 2 or 3, and if it's non-metal, it's going to take in an electron or 2 or 3. Those are monoatomic ions. And I might hear some groaning, but silently groaning. There's those other ions that are like sulfate, sulfite, nitrate, nitrite, phosphate, phosphite. Okay, those 8s and ites usually, that actually have more than one atom that are joined together. Okay, they're polyatomic, and they run around with a charge. So, for instance, everyone loves nitrate, NO3. Actually, some of you guys know that NO3 collectively, those 4 atoms run around with a -1 charge. So they kind of look like, and this isn't drawing the complete Lewis structure of this, because we can draw what we call a Lewis structure of ions like that. But we have a nitrogen in the middle, 3 oxygens all running around with, remember I told you that if you have something that's charged, you put that puppy in brackets like that, and you put the charge outside. So that's just one example of a polyatomic ion. And so we'll be making ionic compounds with those too. And I'll give you a list of ones you need to know. But in the meantime, just what we just covered in part 5. Okay, I'll give you a minute to go ahead and fill these in. These are group A elements, metals or nonmetals. Don't be shy to look at the periodic table. I need to look at the periodic table. I've been teaching this for too many years. So some of you see I did go ahead and just put them all up on there. But it's just what we've been talking about. So in tomorrow's lab, I'm going to count on you knowing what charge these form. Any questions? Okay, so these are ions, but they're monoatomic ions, which is cool. Monatomic ions. So one of the two things you need to get under your belt for general chemistry is for ionic compounds, you need to be able to write the formula, and I don't think we'll get to it in lecture today, but we will in lab tomorrow. You need to be able to give that ionic compound a name. So write the formula of an ionic compound and to name it. Okay. But when it comes to writing the formula, a few things. Okay. Let's see. We kind of talked about the neutral, same number of positive charges. There are negative charges. That's the neutrality we talked about. Net neutrality, no. Neutrality. And then the other thing, I guess that's not. I thought it said. I don't see it on here. Maybe it's on the next slide. But usually, when you write the formula for ionic compound, usually it's the cation first, and then the anion. And like this says, use little subscripts to say how many. Subscripts down here to say how many. Oh yeah. And the other thing, well, I guess not, but it must be on a slide coming up. Up here, I'm going to draw a little circle where we're used to seeing the charges of the metals and the nonmetals. You do not include the charges up there. And I don't know, every year I bump up against this, and I'm not quite sure why students want to include that. That's kind of the diagram of writing the formula of an ionic compound. Okay, there it goes. Typically, you don't show the charge. So that was my little my little circle up there with the X through it. Don't show the charge. See, I got ahead of myself. Cations first, usually anions last. This bottom one down here, so we're going to use subscripts. You know, we're used to seeing like H2O. So the subscript 2 in front of the H says how many hydrogens you need. So we're used to using subscripts. And here's the deal. For instance, let's pick on barium nitrate. I think it's insoluble. Okay, so for barium nitrate, I would know that actually, and we'll talk about why this is, but the neutral formula actually is Ba, and you need 2 NO3 units. So that last rule is simply saying if you need more than one of an ion, and that ion is polyatomic, then you basically nest it and put the little subscript outside of it. Okay. So some of you have already kind of been exposed to this, but let me go ahead and show you my favorite method of doing this. It's called the crisscross method, if you haven't run into this before. What crisscross says is basically you take the magnitude. Well, so for instance, when, let me change my color here. When potassium actually is a 1A metal, and so it'll lose that valence electron, form a +1 charge. So that's all cool. So when we see just a plus, really that's a +1. When we see a minus, really that's a -1. So in the crisscross method, basically what you do is you take the number of the charge on the cation, and that's the number of anions you need, and the number of the charge on the anion, and that's how many cations you need. So you just kind of see the crisscross. Okay. So in the answer key then, of course, it looks like this. K1Cl1. And sometimes, especially you guys are probably like, oh, don't put the ones there. And I'm like, oh, that's harmless. Okay, sometimes students feel good about putting the ones there, but you really don't need them. So the crisscross method for the next one, again, you should be able to look at the periodic table and know that aluminum is going to lose its 3 valence electrons, form a +3 charge. Sulfur's going to pick up 2 electrons, get an octet, form a -2. So the crisscross looks like this. All right, I'll do it like this. The number of aluminums I need is the charge on the anion, and the number of sulfurs, or actually sulfides, I need is the charge on the cation. Not bad. Yeah.
Why isn't the aluminum -2?
Because it's clear over in 3A. Aluminum. So it's actually got 3 valence electrons.
Okay.
Yep. And so for the next one, actually you wouldn't know, I'll put a question mark here, you wouldn't know, because we just said just today that iron can form a +3 or +2. So I'd have to tell you that. But aside from that then, doing the crisscross, the number of Fe's I need is 1, right? And the number of BRs I need is 3. Okay, so the crisscross method, there's just one little catch to it, and actually it's coming up. So otherwise it works really pretty good. And I'm not really pleased about this. It looks like they're kind of spreading apart. They should be closer together. Okay, so crisscross for the next one. The number of AGs you need are 2. The number of oxygens you need are 1. Okay. Up here, the number of NH4s you need, 1. Feel free to go ahead and put that in parentheses if you want. The number of F's you need, also 1. Now, the catch comes for this one. Okay, if we crisscross a copper 2, again, if you find copper on the periodic table, it's kind of like iron. It's kind of like the Fe2+, the Fe3+. Copper, I know, forms a +1 and a +2. It's probably got more oxidation states than that, but I would have to give that to you. But the point is if you crisscross, the number of coppers you need are 2, and the number of sulfites, SO3, 2 minuses you need, is also 2. Okay, and of course that came from that. Okay, so that's my crisscross. So here's an example where actually this is not quite the right answer. If you have, like we have subscripts, don't count that 3 because that's part of the sulfite, okay? But we have subscripts of 2 and 2. If you can divide through by a whole number and get another set of whole numbers, like if we divide through by 2, we get 1 and 1 respectively, you have to do that. So to clean this up actually, it would look like this. Cu1, SO3, 1. And it kind of makes sense. Remember we talked about that ionic compounds, all of these actually are those crystalline lattice structures, and you really can't tell where one ends and one begins. So it actually has to be the lowest set of whole numbers. So to finish it off, looks like the next one, we have what, Li2, SO4. And then the last one, we have Mg1. And we need to put parentheses HCO3 outside the parentheses 2. Y'all good with that? I really like the crisscross method, other than you have to kind of go back and clean up things every once in a while. Cool. They're kind of fun. So there's what we did. So like I said, for ionic compounds, I need to be able to write the neutral formula unit and need to be able to give it a name. So the names go just like it's written. So just like you always write it with the cation and the anion, you always give a name to the cation and a name to the anion. So it's not too bad. There are just a few little pits. Okay, and actually this is alluding to okay, when it comes time to naming that metal that's lost electrons. Okay, some metals only have what we say one form, only one form. Okay, and those metals are right here. Okay, metals that only have one form. They're the group 1A metals, the group 2A metals, skip the transition elements, the group 3A metals only have one form. Also kind of buried in these group B elements, there are 3 metals that also only have one form. Those are silver with a +1, loses 1 electron. Zinc and cadmium both lose 2 electrons. Okay, so this will hopefully make more sense in a minute or actually tomorrow. But here I'm going to say no Roman numerals. I don't know how to spell numerals, so I just put NUM. Okay? No Roman numerals in the name. And that's one of the biggest pitfalls of giving a name to an ionic compound is what do you do with the metal? Do you give it Roman numerals or not? Okay. So, an example of things that do form more than one stable cation, we really ran into iron a little bit ago. Iron, we said, can form an Fe2+ or an Fe3+, and actually there's a reason behind that madness. There's a reason for that madness. So in that case, you do need to use Roman numerals. And some of you maybe learned it, so I'm going to put use Roman numerals. Some of you might have learned, for instance, and I don't even know which is which, in my notes for the lab tomorrow it says which is which, but iron, the Fe2+ and Fe3+ is like ferrous and ferric. I'm like, I have no idea. Instead of that, for the iron 2+, I do iron Roman numerals 2, and for the iron 3+, I do iron Roman numerals 3. Okay? So those Roman numerals, like it says here, are actually giving the charge. And actually, if you want to circle that a few times too, notice that what the Roman numerals don't do is to give you the number of that cation in your formula of the compound. They give the charge. Okay, so that's a real common mistake. Okay, so I kind of summarize it here. That's one of the biggest things. And it's on your Unit 4 exam, you're going to, we're going to kind of see how good we're all at this with regard to ionic compounds, writing the neutral formula and then giving it a name. And these are usually just worth 1 point per compound. So if you put Roman numerals there for the name and it shouldn't be there, then you miss it. And if you don't put it and it should have been there, then you also miss it. But hopefully we'll get some try at that tomorrow. So one way to think of why you don't use it for the 1A, 2A, 3A, and zinc, cadmium, and silver, because you can hang your hat, I use that phrase, you can hang your hat on the charge that they form. So you don't have to use Roman numerals. There's no guessing. You just need a periodic table to know what charge it is. For the other ones, like, I don't know. You have to use Roman numerals to say what charge it is. So then it goes something like this. Maybe to work this, actually, if you find barium, let me make sure I got this right, because I get oh, darn it. Barium's a group 1A, so my check marks actually, you don't have to use Roman numerals. See, I should have looked at my periodic table. All these check marks, now I get magnesium and manganese mixed up, but magnesium is the 2A element. So where the check marks are, okay, no Roman numerals. No Roman numerals. And by the way, barium, like I said, it got me. I thought it was a group B element. But it's a 2A, so yeah, no Roman numerals. But for lead, yes. And for cadmium, yes. And I have no reason why I need to go ahead and remove that from my slides. That really shouldn't be there. Okay, so it looks like this. Only for the lead and, cadmium, it got me, dang it. Cadmium is a group B element, but it's zinc, cadmium, and silver. Oh, boy, I'm rusty on this stuff. Sorry. So let me go ahead and put a check mark there. Oops. That's okay. I'll remind myself how it works. Are we okay? And like I said, let me emphasize, zinc also falls into that category, and silver. Okay, so those are the exceptions. Okay. Any questions? That's pretty good. What would be next? Oh, just another one of those? Okay, all right, so let's take a look at the next one. Let me go ahead and you can take a look at them too. I'm going to put checks next to the ones that you don't have to use Roman numerals. Let's see if I get them right this time. No Roman numerals. No Roman numerals. Yeah, I'm liking that better. Okay. The last one really shouldn't be on the slide either. Any questions? And what are the Roman numerals? It's the charge of the metal, the cation, the number of electrons it's lost. And that's a great place to get to, because what's the next slide? Yay, polyatomic ions. So we are in really good shape tomorrow to crisscross kind of right off the bat. Tomorrow's lab has 3 sections, and it's kind of like that cooking show where he goes, bam, he kicks it up a notch for each of his sections. So the first section is the basic, the second section makes it a little harder, and the third section in tomorrow's exercise actually goes ahead and brings in polyatomic ions. So a lot of what we covered today we'll just reinforce tomorrow. Okay. So yeah, it's looking like a storm of brewing with regard to problems that are going to be due. I'll see what I can do. All right.